We're connected. Hello, friends. I'm going to go get some water, and tonight we will be continuing to, let's do this. Continuing work to lower, to generate VM from our bytecode, not from our byte tree. Can I make this bigger? Oh, maybe I could set the tagline. That would be really cool, wouldn't it? It's a little noisy down there, but at least it's something. Yeah, if you've never tuned in or seen any of the videos before, I'm just working on a compiler for a like systems level programming language. The thing I have immediately decided to do is replace this type has kind of evolved, this compiled unit in the bytecode to essentially hold a type that I need somewhere else that I'm calling a physical function type. So I'm gonna make that change and plumb it through and see what breaks. So yeah, you'll just want, and then what the consequence of this is if it's not a function, but instead an expression, we're gonna treat it more like a function than we did before. So this one is the expression. So we're gonna be like, let this fun type equal, oops, physical function type. See what he has. So that one we already have. The params is going to be an empty slice. ABI mode, we don't have anymore, but we need that. Oh, actually this is not a real function, so we can say internal, and the built-in kind is none. So that's perfect. A bit of a generalization here, but it's gonna help a lot to be able to just refer to that physical function type for all compiled units. Built-in kind. Right. Gosh, we don't know. So I guess it's not really part of a function type, is it? Why did I want to add the built-in kind to here? I need it. So what we're really working on is this file, cogent LLVM new. Go get the built-in type from the bytecode. Okay. Because I think that it doesn't go on the function type, just on the compiled unit. it's not really part of the function type. It's more about the function. Function type is really like inputs, outputs. Like if you were to have a lambda and say, what type is it? This goes on, this is just a new thing on compiled unit. I'm just gonna say function built-in. If this is a built-in function, then that's what it is, which means this needs to take it built-in. Kind option BC built-in. How are you doing tonight, my one viewer? Built-in kind. Function built-in kind. I would say I'm doing well. I had a bit of a long normal week. Excited for Christmas. Glad that it's the weekend. If it's a built-in, right. Well, I already have a place that I determine if a function's a built-in, but I think I need to factor it out. So that's gonna be whatever, because you're definitely not a built-in, but it's where I code in a call. So this is gonna be typed expr call. This is where we turn a call into a bytecode call. And what I do here is we check if it's an intrinsic operation. And yeah, so it's like, it's a function from intrinsic op essentially to BC, to maybe a BC built-in, I think. Yeah, so I could apply that one first, kind of. It's interesting. What I almost want to do is match on this and like return some specific enum of like who should handle it. Right. So what I'm doing is I just want the LLVM, the new LLVM backend, to be able to know which built-in, in terms of the bytecode set of built-ins, the function is, in order to dispatch successfully to basically this guy. It's very silly. Well, intrinsic to built-in, and these names aren't even meaningfully different. It's just what I happen to call it in the prior phase. It should probably be called a built-in there as well. Then it's like typed built-in to bytecode built-in. So let's just maybe this will do for now, even though it'll be duplicated, right? So this is the thing I wanted to avoid doing twice. Yeah. So this is kind of probably what we'll just use as our starting point. And so these unreachables are all going to be none. And these returns also be none, but let's just like invent a type. So enum like function handler is like BC lower typer or BC built-in. BC built-in. This makes sense. So these were handled in the typer phase. These were handled in the typer phase. These get handled. These are BC lowers. And the code that I copy pasted is actually, no, then that's a BC built-in. Okay, yeah. And I really don't want this all to be underlined. Great. So we're saying we're trying to function handler, and I just want the green squiggles gone. All right, nope, they're back. I hate how the Rust LSP does this. Maybe I can do even better here. BC, this is getting lowered. Let's do this. This is so frustrating. I don't even know if this is gonna work. Yeah, it's still gonna be all green. Gosh. This is gonna be BC built-in. Oh, sorry. I wonder if I can use like as H. Promise it's gonna be nice. Basically just codifying what the current function does with this enum. And all right, and now we're on to BC built-in. All right, and now it's gonna start to look prettier again. So, yep. Now we gotta fix the indentation. All right. So, categorizing which functions get lowered by which compiler phases. And then what I would like to do is actually make this use this from the giant match we were looking at before, instead of duplicate the code. So then we would need, for everything that's handled in BC lower, value. I could do it like this. BC zeroed. I think it's not that bad to do it this way. BC bit not. BC bit cast. Yeah. Just these. And now what I'm essentially going to do, a couple of these needed to keep their payloads, but that's fine. And it's not really function handler. It's like, I don't know who to handle, but that's fine. This can be BC big static value. This can just be BC zeroed H. It's fine. Is that really one? Yeah. BC earth bin up, and this is the one that needs kind. That should just keep it, and then this is kind. BC bitwise bin up kind pointer index BC pointer index. Okay, so you need intrinsic arith op kind, intrinsic bitwise. Okay, so why did we do that? So that we can call intrinsic to built-in on f dot intrinsic type equals match f dot intrinsic type none. We're going to call it on I, and if it happens to be BC built-in, match to built-in, and it'll be like this. If it's a BC built-in, then we're some BC built-in, and for all of these cases, we are none. Okay, and now we finally have a built-in kind, and you're mad because you need a fizz function type. And fizz type, oh, I actually already have one, and that got nicer. And now all we have to do is actually call, yeah, we don't have f anymore, even though we already borrowed it twice. Let intrinsic type, we'll just copy it out, and then instead of matching on f, just intrinsic type, and then that's fine. Be honest, half the reason I'm streaming is so that I focus, even though no one's watching. All right. Next, call our function. Typed expert call. Lowering this guy. So what I'm going to do instead, if I have an intrinsic, all of this code is going to be replaced. Let built-in equals intrinsic to built-in, intrinsic. Okay, actually, now we're going to match intrinsic to built-in, and it's not really intrinsic handler. All right, and here's everyone back. The gang's all here, but now what we have is, all right, these are all handled by typer. So now these 6 cases that we know were handled in the prior phase, we can just have, that amounts to 1 unreachable because they were handled in the typer phase. So that's kind of nice. For built-ins, we know we're just saying some built-in. And then what we were doing for the others is, for the ones that we handle, we're just directly doing the code gen we need to do for that operation. For zeroed, for example, this implements zeroed, and then we return. So I'm just going to keep following that pattern. So here's big static value, and that's going to go right here, right? And then I'll grab zeroed. And bytecode built-in is now a bad name for it. BC is where it's defined in this layer, but really what we're saying is it's something that we don't handle in the bytecode layer, which is kind of interesting, that we just sort of like pass the buck to the next phase. The backends are supposed to. So really we could call it a backend built-in. I actually kind of like that a lot. Because then if you look at it, we can say, here are the things that a backend has to provide for NK1. So I'm actually going to go ahead and do that even though things are broken. This is a backend built-in. I'll save all that. All right. And BC. Yep, so you're done. You guys are all done. I did you two. I did you. Bool negate is here. And bit not is here. I don't know if bool negate needs to be. I'm just trying to think if that can be implemented in terms of something we already have. It's like a plot. I guess it's equals. Yeah. Do you check if it's 0? I'm just trying to think of a bitwise operation or something like more primitive that you could implement Boolean negation in terms of. It's not coming to me without having a branch. So what we end up compiling this to is a bit not on an I1, which I do think is better. And so here's bit not. It's supposed to say return. And now bit cast. Bit cast is interesting. So these could all be pulled out, and they probably should be, because this function is really hard to read. This one's nicer, right? Because we just have op, bitwise. Bitwise we did right here, okay. And pointer index, this is our gep. And then backend built-in. Oh, that rename is so good. That rename is good. Match. Ah. But. All right. And then if there is a backend built-in, yep, I make sure and grab the function ID. And that's it. All right. And then if there isn't, all right, that was all of our cases. So wait a minute, because everything returns. So now these don't need to be sums. Wait. Oh, it's only in one place and it doesn't need to be sum. And it's not, so it's no longer an option. So now, and we called it backend built-in. So I can remove this. Yeah, like obviously that. All of that? Why is this not happy? Because we were already in a match. Oh, just because I was missing one arrow? Yeah, okay. So this is really nice now. The only bad thing is how these are all done right here. Because we're already kind of deeply nested inside, like handling calls. But I can worry about that later. That was an existing problem. So what did we achieve? All I achieved is that, right, we know what the built-in is. Now if we go back to Cogent LLVM new, go get the built-in from the bytecode, we can do that. So now let bytecode unit, K1 bytecode functions get function ID dot. We're gonna unwrap, because we should have one. And this is gonna be BC unit dot function built-in kind. And if it's a built-in, then we're going to call Cogent built-in function body, built-in kind. And that's weird because we already copied it out. Is it like, because, no, it's definitely copy. Oh, because this thing's borrowed. I don't think that this thing needs to be borrowed, right? Like this guy can fend for himself. He can just, like we can just go get the function again. Oh, and we don't even need to, okay, yeah. We're gonna do it inside here. Oh, this thing was already grabbing the bytecode unit. That's nice, that's nice. That'll be better. So this was just called function. We're just gonna call it that. And that way we have the span. And we set, that's kind of like our little prelude. I want to separate that. Okay. And I do have a no commit here because I don't, this is just boilerplate. I could probably write these in K1 and just call them from here, which we may do. Okay. What's next? Right. I said that we already had that identical line, which we do. And that's great. So this feels like a really clean branching on the bytecode bytecode unit. If it's a built-in function, generate the body yourself. Otherwise, like compile the blocks. That's really nice. We debug pop scope. Did we push? We did push scope. So that's that. So as part of this, it will be addressing compilation errors. Addressing final compilation errors. How many do we have? Only like a dozen or so. No, 50? No, sorry, 27. All right. 10, all right, 10, make it bigger. No, 10, make it bigger. 2, make it bigger. Yeah, okay. Can't move out of a shared reference because instruction of all things being 48 bytes doesn't implement the copy trait or the clone trait. I mean, it does need to get smaller, but I think we got to do it. Sorry. All right, we're on borrow checking errors. Addressing, so we'll go with appeasing. Appeasing le borrow checker, as you do. All right, so this thing could now just take a fizz function type. Because, what are these three? The params, the return type, and the ABI mode. Oh, hey, look, there they are. So we just basically pulled this out into this shared idea. This fun type. That's fine to pull it out. I think I probably use the ABI mode one more time. Yeah, so let's just pull that out too. I don't mind at all. I don't mind. And param types. Let's pull your reference twice. That's fine. We'll just go ahead and pull out everything. Params. Okay. That's not a thing anymore because that's an intern slice from program bytecode. So we're going to self bytecode them get in. The iter would be here, but we can skip it. All right. Where's our physical function type? Oh, that's clean. That got better, didn't it? Okay. Bytecode fun. So now this is the normal case. Make cogent function type. Bytecode fun dot function type. Oh, yes. So now make a cogent function type only takes a physical function type from the previous layer, which is a sign that I think that we've pulled things out correctly and done a good job. All right. Yeah, that does take self in this. Technically takes self. I could try the one that borrows statically. Yep, and it does work. Okay. Not gonna ask any questions. This returns. Basically, it lets me iterate over things inside this memory pool, notably without having a borrow to self at all, because I know I'm never gonna free these, so I just trick the borrow checker, and return a permanent permanent slice. Okay. Because I'm more interested in building this compiler than never having a memory bug. Yes, I am building a compiler. I don't think this guy ever gets called now. Shoot, so this is a place. Gosh, this is so frustrating. 20. Let's just close him. Yeah, so this is just like old style code that we do still need to support for our static value system, which is a little unfortunate, but it's also not too terribly much code. I think that what I'll do, I'll get a CG type from here by, I think that I could probably get a physical type from the integer type pretty easily. Cogent type wants a physical type. The thing is, an integer type, I could very easily just have a function on here to go to a scalar type. Scalar, get scalar, oh, I already have it, okay. So we have get scalar type. So now we just need a fun get PT. PT is physical type. It's just used so many places that that's just a common abbreviation. And then this is just gonna be physical type scalar of self get scalar type. And now for here, this is easy because then I can just integer get type dot p. Wait, that's a type ID. Wait, it's an int value. Get integer type. You dog. Okay, now we have, this is what we now call a cogen type, and then that's an LLVM type. And the LLVM type is just the cogen type. Rich type into int value into int type. That's fine. Okay, and now we're checking if it's signed, but we already have it. So all I have to do is look here. Integer dot get integer type is signed. Is this a good way? Like, gosh, I do this in like 9 places, like in earlier phases, and I would love not to do this way here, but I would love to reuse some of the code from the other places that I do this, but I'm just not entirely sure that it really makes sense. K1 is getting crazy. Yeah, that's right. Well, I'm kind of frustrated right now because I have I'm really happy with my current to-do list of things I want to do for metaprogramming, some LSP stuff, what I want to do, zero size types, but it just things that like make the language more featureful and better, but I really have to rewrite this backend in terms of the bytecode to reduce code duplication. So, but it's almost done. And then it's going to get crazier. Right now, it's just getting to be a little bit less code in the compiler, unfortunately. So we can do the same thing. So this is going to be float dot get. Hopefully, well, did I even need the CG type? I guess I did because we're using that to get to the rich type. So that's fine. We'll do it that way. Get scalar type. I mean, we'll just go physical. This is scalar. This is not a good place to do this, but I'm just doing it here differently because I wanted to, and this is a CG type. So, and then we're gonna do the CG type dot rich type into float type is the LLVM float type. CG type, sure. And then we're gonna get a const float, and then that's that one done. All right. All right, and then global. What else do we have before I move on to globals? Borrow checker and declare LLVM function. We're not using the ABI mode anymore. That's interesting. Oh, this is gonna be so fun to debug when it finally works, and well, when it finally compiles and nothing works. Sure, why can't I just grab the function span earlier? All right, and that was that. That was simple. All right, and we have these. This is frustrating. Oh, I hate this so much. Do I still need this? We look up by name in the LLVM module. All right, but what I can do instead, I can actually remove this hack. And instead of looking these up by name, when I implement the built-ins, well, that would be a reason to write these in terms of K1 code, but yeah. All right. Let me just, because there's a place where I look up memset in the bytecode. Let memset function ID. Right. So I wonder if I can replace a hack with a slightly better hack and just do something silly here where I would say find well, these would be in mem, find mem function. So, and then basically I'm going to do what I did in there, which is going to be self K1 functions and with IDs if it's mem and if it's memset. So then I need an ident. Ident. And I don't know what this means. You cannot find macro b ice. Okay, well, can we just return none or something? Option function ID. Did that work? Oh, we don't even need to let's just do this. Right? Okay, did I do it? Replacing hack with a better hack, and I think we have, where's exit come from? We have free, and then the last one that we look up this way, exit. And intern fun exit lives where sys. So this is going to be find sys, find mem function. I promise this is better than what I was doing before. And then it's going to be self k1 scripts mem I don't have sys. I'm gonna add it. And it's gonna be fine. F.name equals ident. And this is going to, this stuff's gonna go away anyway when I change where I implement these backend built-ins. But for now, I think that this will be fine. So now we just look for mem everywhere we do mem scope ID, and we'll just try and let is sys. So as we're compiling, once we find sys inside of core, sys is sys. So now we the compiler's aware of the ID of the sys scope, and we can go back to codegen LLVM new, and we can actually use sys scope ID. So now no commit, yes, we're definitely going to do that. But for now, let's just self.declare LLVM function malloc fun ID, because I do declare it, right? Extern fun malloc fun malloc. Yeah. And I wasn't calling these versions, which is interesting, but now we will be. So, oh, but they're in libc. Shit, they're not in mem. Oh, but exit's in there too. Oh, yeah. I don't want to. If I was calling the ones I was planning on looking up, it would recurse. But this is great because now I can just find libc function. Libc function ID, and this is not going to be mem or sys, but libc scope ID. Sys libc scope ID. And oh right, I need sys. Oh. And I can do pub libc. What's the matter with you? I wonder if one could possibly factor some sort of pattern out from these few lines of code. The world may never know. Oh, I missed one. That would have sucked. Again, it's going to go away. We got to focus. We got to focus on the task at hand. Malloc fun ID is self dot find libc function ID. I like that this is in here because it's this backend's particular concern to find this function. And yeah, I think that's okay. So, and we're going to malloc. Malloc ident. We could just call intern. K1 ast idents intern malloc do it this way, else a fine error, just fine. And we ignore the align, which is funny. So probably another reason to do something better here. What now? Yeah, we don't look it up by name. Does this return it? It does. Malloc FV. And then we're gonna call, wait for it, malloc function value. Oh, that is the function value. There we go. So we had to add some hacks so that we could remove some other hacks, but it means this can all go away. So hopefully, yeah, I'll agree that that was good. And we'll go ahead and do can you do this? And instead of let f, can I do let calc? I hate, oh right, we needed to declare it. I don't like that it wrote it that way. Okay, let's just unwrap it. I don't care. All right, calc function, that's why. And we're gonna call calc. And can I do this but for realloc? We're so close. Let's do free. Realloc. Free. Free, 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 free FV, free FV. Epic. Thank you. Okay. Yeah, we're gonna remove all this. Oh. No, mem copy. Ah, this one's great because LLVM does it for me. I don't know why it has a build mem copy, but it does. So that's great. I think it even has a build malloc. Self, builder, build, realloc, build malloc. It gives you a malloc, but no, nothing else. Okay. Mem equals, this is looking up mem cmp, shoot. So I need to declare that too. I'll declare that in libc, that's fine. Mem set is built in. Yeah, all right, so mem cmp, that's fine. We can do this the same way we do our others. Let me go grab one for a mem cmp. I don't expose a mem cmp, I expose a mem equals. Obviously you can just call libc if you want, but the k1 built-in that's required is mem equals. And I think that's kind of nice because it's a lot easier to use. It's a lot less confusing. Ooh. Did I mess that up earlier? Realloc, realloc, calloc, calloc, malloc, malloc, free, free. No, I think they're all okay. Mem cmp I done. Oh, I didn't use /g this time. MCMP fun ID. MCMP FV. You test all these changes or just the compiler in general? That's a good question. Oh no. Now that my IDE's frozen because I pressed a button I didn't intend. Right, yeah, I just blew it up again. I don't know what that is. Let me just quit everything. All right. So I have, the way I test the compiler is how I test these changes, and it is that I compile code. So here in the test sources, I have a number of different suites in here of K1 programs. These are actually ones that all fail to compile. Here's a test for the standard library, but mostly in suite 1 we have, this actually all compiles to one program. So these are just like files in one project, you could think of them as. And yeah, I just compile this project, and all of these files contain many assertions. Actually, these two that I opened, okay, they contain very few assertions, but rest assured, most of them, yeah, contain a lot of assertions. So if anything's broken, this test suite does not pass. It's pretty comprehensive of everything I've done so far. Now I'm sure there are gaps, but that's pretty much how I test the compiler. I compile a big ol' project that basically exercises everything I've ever worked on. And I run that entire project at compile time and runtime. And all the assertions run for both. And it's actually a pain because it's hard to get it incrementally working again. It's kind of like nothing passes and then everything passes again. It'd be nice to have a little bit of unit testing, but it's really just not worth the infrastructure and harnessing you need to cover that stuff. So it's mostly just like full-blown integration testing. Exit. Oh, but memcomp is memcomp is in C, so nslibc. Oh, it's there. Great. Okay. That's everything we've called except for exit. And let's do exit. So that's those three. And then F is exit FV. All right, and this is that error that was in Cogent Global. So let's do remove all the unused imports, please. Remove all unused imports. Remove all unused imports. Okay. So now, tell me what's actually wrong. How many errors do we have? We have 20. Okay, that's not an error, but appreciate you looking out for me like that. And I feel like a compiler could also be imported, right? And it already is, so that's great. All right, we're back to Cogent Global. I don't care about you. All right, static value gen. Yeah, this is gonna be fun. All right, that's fine. Let pt self k1 types how do I do this? Compile type, compile physical type, compile physical type, type ID. Really, all static values should start using physical type instead of type ID, but that's okay. We'll do this for now. We'll unwrap it because all static values have a type that is physical, and then this is going to be our CG type, and that's going to be Cogent type off the physical type. So we kind of got 3 layers of types here. We have our type ID. So the K1 type, oh gosh, the K1 type has kind of the physical types you'd think of, but then it's got some more abstract things like function pointer or lambda object a static. And then we have a generic, which is not really a type at all, but a way to make a type. Type parameters, function type parameters, some implementation details of how inference works, unresolved, a recursive reference. We don't want those. And then we have physical type, which gets a little bit lower. It's either scalar or an aggregate. If it's an aggregate, then I say a little bit about whether it's a union or a struct, things like that. Scalar, this is all we have, and that's pretty good. And then coming down to Cogent LLVM, we have the types that LLVM knows about, which is quite a rich type system, actually. And this can just be cg type.rich type, cg type.rich type, const 0. That's not bad at all. You don't need to borrow. That's my favorite error fix. Oh yeah, this doesn't really change, but is it playing off my physical type? Yeah, K1 type get struct layout. So this is going to be subtype get physical type. Wait, get physical type and compile physical type. Oh, I wasn't supposed to use that. Compile physical type. It's supposed to just be get physical type. Shh. Okay. Yeah, I don't have CG types anymore. I deleted this this class. So this could be a problem. Maybe I think I can go off the physical type. So I'm gonna go off the enum physical type, and I'm gonna cogent type the variant of the enum. So no, this is gonna be K1 types dot get physical type of the enum variant, and we're gonna unwrap it. So we have a physical type. It's gonna be an aggregate though, so we're gonna expect an aggregate, and then that's the enum aggregate ID is what I usually call it. So then, Chris Latner has a new IR. Yeah, I do know that. The old MLIR. Yeah, I want to learn it someday, but I don't know. Need to come to a stopping point with this stuff. I think for what I'm doing, it's not really too helpful, but certainly for what they're doing, targeting all sorts of like accelerators and different GPUs, and yeah, it's super, super important. I know he's really in love with the idea and the design of MLIR. I just need to like grok it. So what I call the aggregate record, and then this is going to be get phys types get mag ID. So now we have this record, and the thing is, it's going to, so how do I do this? I have this, and he yeah, the stuff they're doing for Mojo, I think it's really cool. I know people have mixed feelings about him, and or maybe overhyping it, but I think it's amazing. And I think the idea of taking Python, meeting people where they are, and adding like static types to it, matrix types, all these known layout types that let you compile ahead of time to fast code for all platforms. I think it's just a great idea. I think it's super solid move. And yeah, Python's going to be like, it's going to do what JavaScript did and eat the world. And the runtimes underneath it are going to get better and better and better. And it's not even going to be Python anymore. It's going to be that syntax with compilers like the Mojo one, underneath it. Yeah. So expect enum variant. So that's what it is. So the thing that I have here, I have an enum, and I don't have the type that the method we're refactoring does not exist anymore. It depended on a type that doesn't exist anymore, but we do have this, which is basically exactly what we need. For an enum variant, we need its tag, we need its payload's physical type, its payload offset, where, how far it like into the struct it starts, and then the whole layout. So that should be plenty. I'll call it variant layout, and then all the code below is gonna break. Oh, I just so I just wrote these two lines, and these are already here. I named it so variant PTID. Oh my gosh, whatever. All right, because I already had the ag ID. Whatever. Okay. So what do I do now? Variant.tag value. So I do need the tag value. Okay, that was the only thing I was using. We'll see. We'll see. So we need the payload physical type. Oh no, that's just this. And we need the, yeah, that's fine. We have the layout. Variant ag. I'll just go ahead and fix it. Fix it like bottom up so that I know I'm not gonna get stuck. Okay, and then now all we have to do is push the tag. So we need to tag LLVM value. So this is gonna be like, okay, what's on variant ag tag? It's a scalar type, but it's not, doesn't have the value. I feel like that's kind of a miss, right? Because for a physical type, yeah, this needs to be, I want to replace this with a typed int value, or I could just do like a new scalar int type. Typed int value I think is best. So, shoot, because this is used in how many places? A few. So we don't know the value here. We know that it's like a byte, but we don't know that it's 4 for a given variant. So we actually need a value here. I could do, yeah, let's just bite the bullet. This should be a typed in value. And this is the same thing, but kind of like actually has values on it, right? All right, and actually, whatever. Let's say I think I support all of these for enums, although I don't know if I support the signed ones, but I don't see why someone couldn't use the signed ones. But anyway, that's going to have caused a bunch of errors, which makes me sad. Yes, we're building an enums physical layout. How do I determine the tag? I think that I actually want the index. Yeah. Why does that make me? It's an ecovec still. This code is such a mess. Don't look. Don't look. I hate this. So it's gonna be, oh, maybe like that. Maybe we already have it. Okay. I will take it. We generate that in the type checker, which is better. It's so much better. Okay. That's a scalar. Guess what? Integer type. It already has one. Easy. All right, and that's those fixed. Who broke? Let's make sure our old codegen does work. Yep, so I need to go to a scalar. Let tag scalar. Something like that. K1 looks really nice. Thank you. I don't really know why I'm working on it so much or so hard, but I do really like some of how it's turned out, and I'm pretty excited to just keep working on it. If nothing else, just to keep learning so much. It's been such a rich project for learning. Boom, that's okay. That broke much earlier in our sesh. This is easy. That's when we replaced everything with the little type at the beginning. Top return info. Oh yeah, this is now fun type, red type, not bad at all. Owner. Ooh, making a stack frame record from, okay. I hope to God none of this stuff breaks. This is the diciest stuff with the VM stack frames. I don't think any of this stuff will be affected. I don't know. If it breaks, we'll fix it. It'll be fine. Scalar to FFI type, right? But you're not a scalar type anymore. But now you are. So I fixed it. And yeah, so who is static assert size? Who's asserted to be size 24? Parse statement? Type statement? Someone got smaller. It's you. You're now 20. I'll take it. Oh, because I unboxed something. Okay, let's keep going. Who else broke? Okay, no, we're just back in codegen LLVM new. We're so close. That's not a physical type anymore. I actually think that I'm gonna just go ahead and do one straight to the scalar type here, because I've called this so many times, and it's gonna shorten how the code. This is just gonna be self dot get integer type that gets scalar type. It's just an alias for that. And sure, so you need to be imported, and now I'm gonna grep for this. And each of you guys can just become like that. It'll be better. Not there. Turns out I was already doing that in a lot of places, so I'm glad I did that. All right, that's better. And LLVM new. That wasn't saved is why it didn't come up. Physical. Right, don't need to remove that. Wait, yeah, no, that's fine. Ooh, all the way to the physical type, that would be cool. That's fine, it's probably too far. Don't do it that often. All right, back to Cogent Global, where this thing doesn't work anymore, because I haven't really even done that function yet. And then we were here. All right, and yeah, and we needed to get, this is what got us here, the variant. I was calling it variant. Oh, variant ag. Now, it has a typed int value, which is a tag. So let's just do tag LLVM value. And that's going to be the variant ags tag self dot codegen int value, which is something we know how to do. Integer. I've changed my mind. Int value. Okay. Why didn't that fail? Oh, because it used to call cogent type. Well, cogent type used to be able to fail. Now it can't. Perfect. Tag. Right, you can no longer directly get the layout of the tag. That's okay. Let tag layout equals variant ag tag get scalar type layout. That's not bad at all. Look at this. This is where we pack the exact byte layout of the constants from the result of the compile time code into LLVM constants, and we have to make sure that they're padded correctly, completely, regardless of, yeah, basically, there's no LLVM type that can express an array of different types. So what I do is a packed struct, and because it's a packed struct, there's no padding. So we have to insert all of the padding as 0 bits. And it works. The linker puts all the exactly correct bits in the final binary, and then you can just load these things up just like enums, like it is the runtime representation. It's pretty cool. All right, and now we're cogenning a 0, which we already did 0, but this is a different one for some reason, but that's fine. Let's just do it. Cogen type, we're just going to, oh, we need the PT, so that'll be the PT. Let PT equals self k1 types, get physical type of type ID, unwrap u. There's a PT, so there's a CG type, and then the LLVM type. Don't need, and it's just the CG type. Const. Wow, that's definitely what I wanted. Const 0. Turn to 0 region global. What? You can't 0. Oh, it needs to be a pointer. We need a pointer to zeros. And I just didn't do it yet. Okay. Well, that's fine. Right, so this is easy. CG type dot is aggregate. What was I doing? Types is aggregate wrapper. Yeah, that's fine. Is this correct? Yes, it's correct. I would rather do the PT though. Is ag. Cool. Woof. How many errors? We're 1 week in, and We've touched pretty much all of the original 4,000 lines, and we're down to less than 10 errors. Let's go to these. Okay, make string LLVM global. We do have to do this. All right, this will just be the same sort of thing. So let's string PT the physical type for our string type, which I could put in built-in types actually. And that would be nice. Let's just do this. String PT codern type string PT. It is a struct. Def type string, by the way, in K1 is a view of chars. A view is a buffer, and a buffer is a length and a pointer. Okay. What do I do now? Char buffer type ID. Make buffer struct uses a type ID. It probably shouldn't. Ugh, make buffer struct. Why do we need it? Oh, because we do it off the type. I mean, but there is no one buffer type. Oh, which buffer? Buffer. Oh. It's like at the end of this push, I just have no patience because none of this stuff is like very consequential. It's just busy work. All right, I'm gonna put 7 more minutes in and get this compiling. We're gonna do the char buffer PT. And this is gonna take a PT. I have declared. Why don't I just have it take the CG type? What do you actually need? The physical LLVM struct. Yeah, let's just have you buffer CG type. CTX. That's all you want to do. It's all you wanted anyway. It's like expect struct. This thing wants ownership though. Oh my god. Maybe. It's called from 2 places. Struct type. We're just taking the actual struct type. Like the LLVM one. Yeah, the Inkwell one. That's what I'm doing. From a length and a data. That's fine. Is this a borrow checker? Yes. Gross. Make LLVM string global. It's only called from here. Well, then let's just have it take the string ID, huh? That's fine for now. I don't mind. Is that what it's called? Ruster? Do you even need mute self? I don't care. Let's not worry about it. Make buffer struct. Well, who all calls make view struct? It's called in one place. View. Yeah, it makes sense. View.type ID. Doesn't really matter though. you could just as soon call make buffer struct. Oh, you don't even need the type ID, right? Because it's just length and pointer. Oh my goodness, it's just length and pointer. Y'all. Yeah. It's fine. This code can kind of like all go away because all we really need to do. I'm going to do it. I'm going to put it in built-in types. It doesn't make it any more built-in, I feel. No, it's fine this way. Let's just do it. View. This one takes the actual struct type. This one can take, you know what, it's fine. View type ID, I don't care. You know how many times have I said, you know what, it's fine the last 10 minutes. Oh, that actually does work. Let buffer PT. The thing is, it's all the same. Like physically, every buffer and every view is the same type. So this is just dumb. Physically, every buffer and every view is the same type. So all of this is dumb. Like, maybe we just we don't even get resilience because we still hard code knowledge of the two fields and their order anyway. So I'll probably just rip this all out. But there's the buffer physical type, buffer CG type. It's just so inefficient too. And then that's the CG type, and then we do expect a struct, and then buffer CG type, struct type. We can get a struct type out, and then that is actually char buffer PT, char buffer. This is char buffer CG type. Char buffer CG type. If you want to debug info, then you do need to do all of this code gen, because we gotta. That's where it really matters that you know what the type is pointing to. But none of this is doing debug info to just build these. But that's okay. We're gonna be okay. And now I'm fixing this name for no reason that I'm gonna get rid of. Struct type. Boom. At least that's there. Int. What? Can't fail. Great. Where are we now? Some borrow stuff. Cogent static elements array because view.kind, let kind, holy. Okay, view.type ID. And then it's also going to be view.elements, isn't it? No, it's just that I'm not using it. Is that fixed? View.elements, you take mute self. Okay. Tried. Love you, borrow checker. It's okay. You're looking out for me. I get it. It's okay. It's not a big deal. It's good. It's all good. Uh-huh. View elements? Really? Why did all of this become... Why did any of this change? Mem. Hey. We tricked Rust again, look. You can't stop me. I'm gonna get my N elements. I'm gonna use them while I also do other stuff. Are you a climber? Nope, I'm not a climber. I do mostly body weight exercise though. Like I do a lot of pull-ups and push-ups, and I try to do handstands. The Ruster strikes again. No, please. No. Let me go. Please. Please let me go. Oh, climbing K1. No, that would be cool. It doesn't actually mean anything. It means my name starts with K and it's my first language. I'm thinking of naming it something else once it's done. Oh my gosh. Like, actually shoot me. Like, who cares? Alright, this variant ag is a very small enum variant layout. I think he's very small. How big are you? Like, oh no, it's 40. Okay, like, it's like not that small. Yeah, I don't know. And then E is also borrowed. So, but that's very small. Static enum. How big is this? I don't know. This I can copy. Is it not? Yeah, I know. And then so variant ag.payload and variant ag.tag. All right, fine. There. And then the size, the final boss. That's the envelope layout. What a grind. Geez, there's no way. There's no way grind like this for an hour and a half if I didn't stream. Okay. Really? Oh my God. Are you done yet? Are you done complaining? I promise none of this is moving. Where's the part where we... Oh, because I did this. All right, so can I... Right, because I'm not even... Oh, but that's going to invalidate it. Right, that's the whole point. Because this is somehow doing mute self. But it doesn't need it. Oh, cogent type does. Oh. Even though all it does is insert into a hash map. All right, so we'll make the copy variant tag. This is what I should have done a while ago. I just, I pulled it out meaning to do this, but I just didn't. Variant payload. Oh, variant offset too. Why not? Okay. What are we still borrowing by the time we call this? Variant ag? Oh no. Is it over? There's one right here because of s.type ID. The struct. Get struct to layout. I see. Fine. I'm just gonna do it this way. All right. I should use the physical types layout, not this, but I just don't care. I think this does go through the physical type anyway. Yeah, it does. It's gonna be slow, but it's fine. And that's it. It's just the cogent global now. Fun type. Return type, what did I have? Return type was none. It's kind. I'm gonna assume that none of this matters for what we're testing here. See, I do have some tests. Internal is what it's called. Missing function built-in kind. All right, and looky here. Yeah, I don't need this macro anymore, that's true. And wow. All we have left is something in cogent global. And that is gonna be it. it's just static values, so it really doesn't need rewritten. And let's not do that. It's going to be self.globals insert global IDs, how I want to do this. And I'm just going to insert the global value. Yeah, so what I did is I made the lookup smarter. So this doesn't need to, yep. This doesn't need to know what kind it is. Yep, so you're gone. We removed some things. All right, so 3,473 lines. The old backend was 4,677. So we lost 1,200 lines. Not as much as I hoped, to be honest. But the 3,400 we have left are a lot less duplicative of everything else in the code base. A lot more directly about LLVM. And that was the goal. And now this is just really angry. Is it all just, it's all just borrow stuff? Yeah. Can I do that? How big is typed global? Typed global. Can I just clone it? 32 bytes. It's actually pretty small. Is it? What? Oh, I guess that kind of makes sense. That takes mute self. Definitely need to do the initializer after we've then I could just reborrow the global or something. Make global from value. Is that mute self? Oh no, I pressed whatever I'm not supposed to press again. Maybe it's GF. I don't know. See, look at this. Now everything's wrecked. What the hell? Like what? All right. Just restart it. It does, because it updates a hash map. I see. Make qualify name, and then we borrow it. Oh, I just don't know. It's just a stupid. Let me just do this. Let's just clone it. Oh my god. And the name, unfortunately, can't have a borrow, so we'll just allocate. We'll just allocate for every global. Once is okay. Does that mean that this doesn't get used? That's nice. Earth isn't used, okay. Let's just deal with these. Interesting. Unused. Right, I ended up not using that. I don't need this type anymore. Wait, really? No, I am using it, but I'm never constructing. What's unused? Here we make a void. I just don't believe that that's true. Right. Is this just the only place? Oh, I'm not calling cogent function call. Ah, because it's to do. To do. There it is. Call. Self dot. Cogent function call. But it's true that we don't need that type. It is true because this should just return to us. Well, we don't even care. We're just going to add it to the inst mappings. Call value. It needs to be a basic value. Well, it's going to be either. Oh, shoot. If it's a struct return. Yeah, so there's more to do here. What do we return here? Yeah, I don't know. Well, I don't think I'm going to be able to end this stream with a big successful. Everything's compiling now. Yep, we built the unreachable. That's fine. Well, maybe I can actually. It's just going to be like everything's compiling, nothing is working. Right, there's your call value. We have a big to do here to actually insert the thing if it worked. And if it's a struct return, if it's a struct return, then I did the alloca. Right, then I did it here, and I need to return that. If it's sred, oh, I am returning the pointer. Okay, so it's only if it's unreachable. So that's like basically just gonna be like if it returns anything at all, then it's gonna be in there, and that's gonna be inst mappings return value. Please. What? Oh, duh. Okay. All right. So, term, cargo, build. 1 whole week. Well, a few evenings. I don't get to work on this during the day. Boom. It compiles. It does not work. Well, we're not calling our new one, so let's see if we broke the rest of the compiler and building the new code gen. VM test, okay. that it? Is that all I needed to do? All right, unit tests. Let's go. And the rest of them. Missing memset function. BC 1488. Yep. That's right. Because it's not in mem. It's in libc. Oh, but I wanted to call my memset. The one in our thing is just called set. And what are my args? Intern fun set. Yeah, I'm calling mine. Let's do it. It can just go here. Pub set. You can do it. This makes sense because it's something I changed in the bytecode gen. Shit. Still? In this mem? NS mem fun set. Maybe we haven't compiled it yet? The thing is, this was already here. I don't know. Yeah, it's too early. No. Set would have definitely already been compiled by now. All right, well. We'll have to figure this out later. Beat. What a sad ending. Well, it is compiling. And I'm sure the old stuff will be passing again soon. I patch up. I didn't change all that much. And then will the new stuff work? We'll find out next time. Good night.